Alright, so here is the second part of 6.4, which is the area of a surface of revolution. So essentially, previously we were finding the length of an arc, and then in the previous section we were finding the volume of revolutions, so turning things around a certain axis. Now we're looking at the surface area of a revolution. So it says if the graph of a continuous function is revolved around or about a line, the resulting surface is a surface of revolution. So it says that you have to have this function. It has to be a continuous derivative on the interval from a to b. The surface area S of the revolution formed is this equation on the next page. So the first equation looks like this. It's 2 pi times the integral from a to b of r of x times the square root of 1 plus the first derivative of f of x squared dx. And r of x is the distance between the graph of f and the axis of revolution. So for example, I can kind of scooch over here a little bit. For example, if you had like a function that looked like this maybe, and you were finding the area of revolution if it was rotating about the x-axis, then the distance, r of x, between the graph and the axis of revolution would just be f of x, because that's the distance no matter where you are, would be f of x. And vice versa, if I can erase this, if you rotated it about the y-axis and you did that as your revolution, then the distance between the graph and whatever point you're looking at would just be x, because then you're looking at the x value would be the distance. So r of x is either, depending on what axis you're looking at, it's either some value plus or minus x or some value plus or minus f of x, to kind of get you into that idea. So back over here, contrary to the first one, if you are rotating it, if you have a function in terms of y, so it's x in terms of y, then this would be the function for that. So you integrate from c to d of r of y times the square root of 1 plus g prime of y squared. So it's the same thing, it's just with y values and y limits instead. There's a example down here, so find the area of the surface formed by revolving the graph of f of x equals 2x squared on the interval from 2 to 4 about the x-axis. So a couple things. Number one, this is in terms of x, so it's y in terms of x, so we know that we're going to use the first formula. I have my interval from 2 to 4, and we're rotating it about the x-axis. So that was like the first picture that I drew. So the distance between the x-axis and the graph of f is, right over here, r of x equals f of x. And so, because if you take the first derivative of f of x, it equals 4x, then you can plug all those things into the formula. So you get that the 2 pi times the integral from 2 to 4 of r of x, which is 2x squared, because that's the same thing as the distance from the x-axis to the function, times the square root of 1 plus the first derivative squared. So the first derivative is 4x squared is that. We won't take the time right now to actually go out and solve this just because it would be a little too much work. So in a calculator I plugged it in and I got 3025.337. So let's look at some examples out of the book. So the first example we're going to do out of your book looks like this. Alright, so the function is f of x equals x cubed, so it's a function of y equals some function of x. So the x values are the main variables in this function. So we're looking at it on the interval from 0 to 1, and we're revolving it around the x-axis. So remember, this is the picture that looks like this. If we revolve it around the x-axis, which is this one here, the distance between the x-axis and the function is always going to be f of x. So we know that f of x is going to be our r of x in this case. So if we set up our equation, I have that the area of the surface of revolution equals 2 pi times the integral from 0 to 1 of r of x, which I just said was f of x, so x cubed, times the square root of 1 plus the first derivative. So the first derivative of f of x would be 3x squared dx. So if you square that out, you get 2 pi times the integral from 0 to 1 of x cubed times the square root of 1 plus 9x to the 4th dx. So I can actually use u substitution here. So if I set u equal to 1 plus 9x to the 4th, then du would be 36x to the 3rd dx. And I have my x to the third and my dx. I have my x to the third dx. The only thing I don't need is that 36. So if I divide both sides by 36, I have 1 over 36 du equals x cubed dx. And if I may erase some stuff, so go ahead and make sure you have this written down. If I can erase a couple things. I also know that my new limits of integration, so when x equaled 0, that was my lower limit, u would equal, if I plug it into this red highlighted equation, if I plug in 0 there, I get u would equal 1. If I plug in x equals 1 there for my upper limit, I get that u would equal 1 plus 9 times 1, which is 10. So when I plug all of these new things back into my original equation, I get that s equals 2 pi times the integral from 1 to 10. Now the x cubed dx is going to be part of my du. So I have the square root, and my u was what was inside the square root, 1 plus 9x to the fourth, so it's just a square root of u, times 1 over 36 du. And that was using u substitution. So if I bring out the 1 over 36, because it's a constant, I get pi over 18, because the 2 and the 36 simplify. The integral of the square root of u is u to the 3 halves over 3 halves, so I'm just going to flip that fraction up like that, from 1 to 10. So I have the pi to 18. If I plug in a 10, I get 2 times 10 to the 3 halves over 3. F of b minus f of a would be 2 times 1 over 3, which is just 2/3. And if you plug all of that into a calculator, you get 3.563 as the final answer. So it was mainly u substitution that we had to worry about in that one, and then just plugging in, knowing what r of x is, maybe is a little bit of a confusing part as well. So let's look at the second and final example. Today's going to be really, really short. Alright, so here's the second and final example. We have f of x equaling x squared on the interval from 0 to root 2 about the y-axis. So this one was like that second case. It's still a function y in terms of x, so we're still looking at x values and we're still looking at y's, or y in terms of x I should say, but if you look at your function this time, because we're rotating it about the y-axis, we want the distance from the y-axis to our function, which is always going to be x, so we know that x equals r of x in this case. So when we set up our equation, we get s equals 2 pi times the integral from 0 to the square root of 2. Now we just said that r of x was x, so we can leave that like that, times the square root of 1 plus the first derivative of f squared. So the first derivative of f is 2x, and if we square that, dx. So when I simplify this a little bit, I get 2 pi times the integral of x square root of 1 plus 4x squared dx. So again, I can do a u substitution. So if I let u equal 1 plus 4x squared, that means that du would equal 8x dx. I don't need that 8 there, so I'm going to move it over. I'm going to get 1/8 du equals x dx. And if I change my limits of integration, when x equals the lower limit, which is 0, u will equal, and again I'm plugging it in right here, u will equal 1. And when x equals the upper limit, which is the square root of 2, u will equal, the square root of 2 squared is 2, times 4 is 8, plus 1 is 9. So I get 2 pi times the integral from 1 to 9. Sorry, it kind of is covered up down there, but hopefully you heard what I was saying so you can write it down. The x dx equals 1/8 du, and then the square root of u goes in here, and this is 1/8 du. So I can bring that 1/8 outside, so I get 2 pi over 8, which is pi over 4. The integral of the square root of u is u to the 3 halves divided by 3 halves. So I'm going to bring that 2 up to the top from 1 to 9. If I plug in 9, I get pi over 4 times 2, 9 to the 3 halves over 3. I'm going to erase some of this stuff over here. Minus f of b minus f of a. If I plug in 1, I just get 2 over 3. So if you simplify that a little bit, you get pi over 4 times 9 to the 3 halves is the square root of 9 is 3. 3 cubed is 27, so I have 2 times 27 over 3. The 27 over 3 simplifies to 9, so I have 2 times 9. That makes 18 minus 2/3. And if you put all of that into a calculator, you get 13 pi over 3, which is about equal to 13.614, like that. So, these two examples didn't necessarily get into x in terms of y, they just simply stayed y in terms of x. So we didn't really have to worry about changing the original interval from whatever interval we were looking at. If it was y in terms of x, you might have to actually change that around, so just be careful about that. But we did look at two examples, one that was rotated about the x-axis and one that was rotated about the y-axis. So that's it for tonight.